Hello, welcome to the first session of the last day. So let's begin the talks. Nijia and Jen will give talk on bounded collision resistant registered functional encryption for circuits. So let's welcome Nijia for
Thank you for the invitation. My name is Yi Zhang, coming from University of Wollongong. And today I will presenting the topic about bounded collision resistant registered functional encryption for circuits. This work is completed under the cooperation from Jie Chen, De Biaohe, and Yujing Zhang. And first, let's start out by reviewing some background of functional encryption. So in this FE system, there are two parties. The sender has some private data X, and the receiver wants to learn a functional value over this data. Usually, the sender can encrypt this data using master public key, MPK, to generate. After receiving this ciphertext, the receiver will use his secret key SKF to acquire the function value. So here, both MPK and SKF come from a trusted authority. This authority will run set up algorithm to generate MPK and master secret key MSK. This MSK is just used for delegate secret keys for different functions. So in this system, for security, we require this server text will not reveal anything except for the function value. And for this function, it can be represented as any polynomial size circuit. And we already have online work for functional encryption for circuits. But we still have a bigger problem. Here, this MSK must be kept secret by the trusted authority. If it is disclosed to the adversary, the system of whole system, the security of whole system will be compromised. So this is the so-called chaos issue. To resolve this issue, a new primitive registered functional encryption is proposed. I will call it RFE for simplicity. Still, we have two parties, but the trusted authority is replaced by a filter. This filter is transparent. It's just the wrong setup algorithm to generate public parameters. Here it's called the common reference string, CRS, and L is the maximum amount of system users. So here, this filter will not keep any secrets. And with this CRS, the receiver will generate a pair of public key and secret key by himself. And then submit this public key and its function to filter. The filter will register this information into MPK and self-secret key, HSK. Here, HSK is useful in the decryption algorithm. So we note that this registration process is fully public and deterministic, and the output of these algorithms are compact, just a polynomial in the size of function and log L. So with RFE, we managed to remove MSK and hence resolve KSK issue. And we also hope this function can be represented as any polynomial size circuits. Then let's go into the security model of RFE. Here we mainly focus on the strong the strongest adaptive simulation-based security. We have an adversary who collude with many corrupted or malicious users and acquire their secret keys from SK1 to SKQ. So even for such adversary, they still cannot distinguish two words. The first, in the real world, the ciphertext is generated normally, but in the ideal world, ciphertext can be simulated by public parameters, and the function values this adversary has known. Although this security is practical enough for applications, but we already have some impossibility results. It is even hard to build efficient conclusion FE for circuits for milled assumptions. So with these results, the research of RFE can be divided into two directions. The first one is the conclusion RFE for limited functions. Here we just list the state of the art coming from Zhu et al.'s work in Eurocapital 24. They focus on simple linear or quadratic function and achieves very selective simulation security. This selective security will limit the adversary to provide the changing information in advance. And this work mainly focused on second direction, boundary collusion RFE for circuits. Branco et al. Has already given a generic framework for bounded RFE. So bounded RFE has several significant features. Initially, it will assume a collusion bound Q. This bound is far smaller than the total number of users L. The setup algorithm will just take this collusion bound as the input, and the security is preserved only when at most Q users are corrupted. Also for efficiency, all parameters will depend on this Q. So compared to standard RFE, bounded RFE has relaxed compactness. Just as I mentioned earlier, although we already have a generic framework from Branco et al., but we still have some concerns about this framework. This framework requires linear RFE, but linear RFE is usually hard to build, and only selective SIM security is available. Then, to our best knowledge, all existing linear RFE schemes provide no post-quantum guarantee, and they usually rely on pairing and have long-size CRS. So all this can be summarized into a question: can we construct a bounded RFE with adaptive SIM security from weaker assumptions? So this is the goal of our work. We want to build a bounded RFE from weaker building block, achieve both adaptive SIM security and post-quantum security. And it also enjoys compact parameters. So our result is exactly a new generic framework. We can build bounded RFE from a new primitive, global registered broadcast encryption, and we also provide two concrete instances from pairing or lattice. Then let's go into the technical path. It mainly has three steps. Here, one bound and Q bound notion means the security against the one or Q public users. And one slot L slot means that in this system, all L users will register their functions into the system in one shot. So at the final step with Q bound L slot RFE, it is very easy to build a bounded RFE just using the generated compiler from Hamburger et al.'s work. So let's start with this basic construction. We want to build a one bound, one slot RFE. Here, only one user will register his circuit into a system. This circuit can be denoted as the bit string, the start of length as n. And we start our start point is the Sahara and Sayulog loop construction. We can build one bound, one slot RFE just from general public key encryption. Then for CRS, it just consists of unpublic keys simple from PKE. And similarly, the user will generate his public key and the secret key by simple unpairs of PKE. Here, each pair of PK and HSK correspond to the circuit base. Then we put all these public keys together to form MPK. Here, HSK is said to be empty. It's useless in this setting. So with this MPK for encryption, the first step is to gobble a universal circuit that takes as this circuit as input, and this will also generate two N labels. We use PKE's encryption to encrypt each label to form the final ciphertext. For decryption, the user can just use secret keys to recover corresponding labels and then evaluate the function value. So this RFE construction is simple and practical enough, and generic enough. It just requires PKE. A natural idea is to extend it is to multi-user setting. That means there are more than one user will register their circuits in the system. Here we consider the user number is 2. We can also we can still place all public keys into MPK and then form the ciphertext by encrypting each labels using public keys. But this method is too trivial. When it's generalized to the case when L is a large number, the parameters will be polynomial size in L. This is too heavy. Then our idea is to replace the PKE with a more powerful primitive register broadcast encryption RBE. So here, the MPK of RFE is formed from the MPK from RBE. Each user can register their public keys into one of these MPK, and so as two HSK and the ciphertext. Here we note that the ciphertext these two are associated with broadcast sets. For example, if circuit 1 and circuit 2 has the same bit at the position W, then both of them can recover the same label from ciphertext. This will ensure the decryption algorithm still works. But in some extreme case, if this broadcast size is exactly L, I mean all users will register into the same MPK. So then the size of all parameters will also grow with L. So RBE is still too heavy for us. Then we propose a new primitive. We formalize the definition of a global RBE. It can be still a weaker variant of standard RBE. They have same algorithm, setup, generation, verification, and aggregation. But the difference is that no matter how many users register in this system, the size of parameters is still polynomial in log L, not growing with number. Correspondingly, the functionality is weakened. We allow all registered users to automatically obtain the decryption access to the ciphertext. So for this encryption algorithm, there is no need to specify any broadcast sets. And the security is just the IND security. It's very weak. We require that this security holds only for adversary who has no idea about any secret key. Then with this solution, we look back to our RFE construction. Here, even if all L users register their public keys into the same MPK, the size of MPK, HSK, and CT will still be compact. As for the security proof, it's also straightforward because we only consider one bound security. I mean, there is only one corrupted user with circuit C, then we can first we can simulate the first half the first half ciphertext by the security of double circuits, because all these n labels are related to to the register circuit base. So this is simulate they are simulatable just using the function value. And for other half of labels, here this particular user has no differential access, so we can randomize these labels just using RBU security. The adaptive and secure GRB can be used to construct adaptive simulation secure bounded RB. So next problem is how to construct this new primitive global RB. For the intuitionally, our first method is to rely on register attribute-based encryption (RAB) because this primitive is powerful enough to cover the functionality of RB. So here we can refer to Freitag, Waters, and Woods generic compiler for flexible distributed broadcast encryption. But this method always needs to set some dummy attribute of policy, which will incur extra cost. So this work we refer to this method to provide a more efficient games. And this dual chips adaptive and security. For the first game is derived from Drew HL's parent-based IB. And the second one is still referred to the transformation from lattice-based witness encryption. Because this game owns more complex parameters like CRS, not growing with user number. So this gave us possibility to achieve IFE with unbounded user's property. So at the third step, we want to upgrade one bound security to multi-key security. So this bootstrap can be done by the approach of Governor Wilkinson and Wade. More precisely, we can set up several one-bound L-slot RFID instances in parallel. For example, user 1 can register his circuit into subsystem 1 and subsystem 2, and user 2 can register into system 2 and system N. So in this case, even for those subsystems like system 1 and 1 and 2, 1 and N, because there are at most one user has different access. So here we can just rely on the one-bound security of underlying scheme. But for other subsystems like subsystem 2, here there are more than one user has different access. So we cannot rely on one-bound security. We need to adopt dynamic reusable MPC protocol, just as the in GPW12. So this protocol needs to ensure that the register set from user 1 and user 2 must be randomly and privately. It should ensure that small pairwise intersections and cover framing is posed. So that's why our final construction is just the property security. For malicious security, for example, this user may be registered the same set into the whole system. So in this case, small pairwise intersections and cover framings will not hold. Then the security will become compromised. So that's why the malicious security is hard to be realized. We will leave it as a future world. Then this is a summary of our paper. We managed to present a generic construction for bounded RFID for circuits. And it just requires a weak primitive global register broadcast encryption. And it achieves the adaptive simulation-based security, and it also has some has two concrete instances of over parents or lattices. And all parameters could be polynomial in log L. Oh, this is all my presentation. Thank you for listening.
Any questions? Just very small question, like just the last second slide. I just want to know how is n dependent on Q? Is it dependent on Q? N. So inside. Yeah, the number n. How does it depend on Q?
Which one?
Yeah.
Oh, you mean the parameters of N? Yeah.
The number n, you have written it n depends on Q. I just want
Yeah, this N might usually to be polynomial.
Any more questions? Let's thank the speaker again. So we'll start this from tomorrow.
I'm Gennaro Tabile. This is going to work with Nico Dortling, Bernardo Magri, Christos Safkas, and Stella Warning. And today I talk about a special type of witness encryption. So, what is witness encryption? Witness encryption is a special kind of encryption where you encrypt with respect to an empty statement, X. So the encryption algorithm takes as input this statement X and the message and spits out the ciphertext. And then to decrypt, we additionally input to the decryption algorithm the witness, such that X and W are in the empty relation. And if that is the case, we are able to recover the message. So we have a witness encryption for all MP. And the security of witness encryption roughly says that the ciphertext reveals nothing about the message whenever X is not in the language. And the size of the ciphertext grows polynomially with the size of the circuit that verifies the empty relation. So people have been studying different notion of witness encryption for a specific language in order to get different security or better ciphertext size. So one of these notions that we care about is signature-based witness encryption, where the witness encryption scheme is defined with respect to a signature scheme, and the relation is a threshold relation. So basically, the statement is a set of n signature verification keys, VK1 to VKN, and a reference message that we call capital T. And then a satisfying witness for this relation is a set of little t signatures, such that each of those verifies under message capital T on different verification keys. And basically then to encrypt, we just specify the statement that is this reference message capital and this set of verification keys and the message. And to decrypt, we just need to input many verifying signatures. And the security of this primitive is formalized as a classic MCTA game, where also additionally the adversary is even allowed adaptive Oracle query to corrupt keys or to get a signature on messages different from key. So one of the applications of this primitive is time release encryption with the help of an infrastructure that is proof of stake blockchains. So in proof of stake blockchains, you have a set of validators that have different signature verification keys. And then through a mechanism, say a lottery, a subset of them gets selected whenever a block is mined. And then this subset of people will validate the block. And if the block is valid, they'll put signatures on the block to certify its validity. And we can use this infrastructure to reveal messages in the future. So let's say that at this point, we have the block 1770 that is mined, and we want to reveal a secret term whenever block 7072 is approved. So basically, we can just use this SWE primitive by encrypting with respect to block 7072 the message that we want to reveal. And whenever the blockchain gets extended, then these signatures appear, then we have the witness to decrypt the ciphertext. So everyone, just by accessing the blockchain, can access the secret. So the current realization of this primitive have been designed with practicality in mind. So they are practically efficient, and they're based on widely deployed signature schemes such as BLS, and they satisfy strong adaptive security notions. But they have a big disadvantage that they have a ciphertext size that is linear in n in the number of keys. And for example, in this application that I showed, you would like to have many, many validators, and this will have, I don't know, ciphertext scaling in the thousands of validators. So what we do in our work is we study whether it is possible or not to get this primitive with the compact ciphertext, say polylog in n ciphertext size. And we answer positively to this question. And we do that without adding any setup assumption. But ours is more of a feasibility result. Is based on I/O for Turing machines and other I/O friendly tools. And still with this strong tool is quite challenging. Indeed, we just achieved a notion of static security that I'm going to show in the next slide. So we don't do adaptive security. So the notion is this one. So the adversary on the left-hand side specify at the very beginning the message, adversarial message T star, and the set of corrupt parties at the very beginning. And this corrupt party is at most T-1. And then the challenger just provides honestly generated keys for all of them and provides the secret key for the corrupted parties. And then only now we enable a query interface for signature generation on messages different from T stars and non-corrupt keys. And then it proceeds like an MCPA game where the adversary sends a pair of messages and the challenger just picks a random bit and encrypts one of the two messages at random, and the adversary has to guess. So this is what we achieve. Now I'm gonna introduce all the tools that we use. So first, I/O for Turing machines. So say that you have a Turing machine of size S and time t that on certain set of input text has a certain output behavior with the output y's. And then you have another machine that has the same input-output behavior, and then the same size and the same running time. Then there is an obfuscation procedure that creates obfuscated version of those machines. And then these obfuscated machines, they still have the same input-output behavior and they can be run. But now, whether I give you the obfuscation of the first machine or the obfuscation of the second machine, this is indistinguishable to you. And two feature of this I/O is that it is efficiency preserving, meaning that obfuscating only has a polynomial overhead, which is useful for us. And one key point that is important in this presentation is that the size of the machines matter, because indistinguishability holds only if the size is the same. So it means that if in your security proof, your machine keeps increasing, then in the real construction, the machine that you have to provide is as big as the biggest machine in the security proof. So the I/O friendly tools that we use are puncturable PRF, puncturable signature, and SSB hash. So puncturable PRF is just like a PRF, but it has an additional feature that one can puncture keys so that these keys on a point X will not allow anyone to evaluate it. And we want this to be functionality preserving, meaning that the output is the same on punctured and unpunctured key or non-punctured points. And we want pseudo-randomness at punctured points. Then we use puncturable signatures that are analogous to signature, but they have an additional punctual key generation algorithm, so that when you give to this punctured key generation a message M star, it will output a verification key VK star, such that statistically, under this verification key, there is no satisfying signature for message M star. And then the rest of the notion is identical to a regular signature. The only additional thing is that we want the regular keys and punctured keys to be indistinguishable. And then we have somewhere statistically binding hash that we can see this as vector commitment that it's computationally binding on every index, but is statistically binding on one specific index that we specify at key generation time. So at key generation, you specify an upper bound on the size of the vector and this binding index. And then there is an hash algorithm that creates a short digest on inputs a large vector. And the size of the short digest is independent of n, the size of the vector. And the size of the key is polylogarithmic in n. And we wanted the index siding, meaning that keys with different binding indexes are indistinguishable. And of course, we have a way to open succinctly position, like in any vector commitment. So basically, with an open algorithm, one can open to one location of this vector and produce a succinct proof that has polylogarithmic size, and the verification time is also polylogarithmic. So now I'm ready to give a blueprint of how we do our construction. So basically, the blueprint is very simple. So to encrypt a message, we first sample a symmetric key of a symmetric key encryption scheme, and then we encrypt the message with the symmetric key encryption scheme. After this, we take the symmetric key and we share it. So if we have threshold T and then keys, we make a T out of n Shamir secret sharing of these, and intuitively each share corresponds to one of the keys. And at the end, with all of this information, we create an obfuscated program that is used for decryption. So, and then the output is a ciphertext and this obfuscated program. And now the decryption works by using this obfuscated program as a share generator. So say this obfuscated program will take an input, the reference message, capital T, an index I, the signature on the KI, and the verification key I. And then it will output the corresponding share if this signature is verifying under VKI for a reference message capital T. And this means that if we have enough signatures, we have enough shares, so we can reconstruct the key. And after having reconstructed the key, we can decrypt. So this is the blueprint that we want to do. And we need, for our thing to make sense, we need this circuit to be small, this program to be small, and we need to prove it secure. So to have it small, we can use this SSB hash, and basically hash all of the keys are the code in the program, just a smaller representation of all the keys. So this program would have hard-coded the hashing key, the digest, the reference message, and this K1 is a puncturable PRF key. And the idea would be that whenever a provided signature verify and the provided key is one of the key from VK1 to VKN, verifying this commitment, we can have the output, the program outputting the corresponding share, and to have a smaller representation of this, we use pseudo-randomness, and we compute the share using a puncturable PRF as a source of randomness. So it's a pseudo-random Shamir secret share, and we can return this share. So is this okay? Is this small, and can we prove its security? So it looks small, but let's try to prove the security of this. So a blueprint of how would you do it. So you start from a machine that encodes all the shares. So it encodes basically the key. So you want to erase as much information as possible from this program so that it encodes no information at the end of your security proof. So The first idea, the first step would be to just erase the contribution intuitively from all of the honest keys, because intuitively the adversary cannot get the shares for the honest keys. So with some sort of puncturing argument, you will delete this contribution. And after you have done that, you would use the secret sharing security to swap all the pseudo-random string with random string for the remaining unqualified set of shares. But this has problems for the size, even though this will be difficult to argue. But even though you are able to argue it, you have problem with the size, because for step one, basically, since these points are correlated, you will need to erase them all at the same time. All of the shares you need to erase at the same time because they are correlated. So from one share, you can recompute the other. So it doesn't really make sense to delete them one at a time. And this makes a punctured key that is too big because these points are at random location. So generally, this punctured key will have to encode this information. So it will be big. And you will have to hardwire all of this random value in the program in this last step, number 2, when you do the switch. So you'll have to hardwire too many random values in the program. So the circuit will be at linear in T, which is too big. So basically what we have now, just a recap, even if you lost what I said before, is that we start from a circuit that is a program that is small. It encodes the information on the shares, so it encodes the decryption key. And with an hybrid argument, we were arriving in somewhere where, yes, we have no information on the key, but the circuit that we have is too big, and the program. And this program in the real world will be as big as this final one. So we don't want that. So we want to arrive in a different situation where basically we use a different abstraction. So the abstraction that we want to arrive to is like, at the end of our security proof, we will have some machine that is a machine that does not compute shares, but it's like a retrieval machine. So in our model, we would have that there exists some private memory somewhere that has the shares, and it's not accessible for some reason by the adversary. And then what this machine does would be just simple retrieval operation. So whenever the signature is okay and the SSB proof is okay, this machine will just send a read request to this memory and will access this share for us. So it will just output the share. So this machine is just performing a small computation that is checking the signatures, and then it's recovering somehow this value from a memory. And if we arrive to this kind of ideal world, then we have a machine that it is small and it has no information on the share. So how do we emulate this real world, this ideal world? So basically, we use a couple of tricks, and we exploit this static security that we have. So the first idea that we use is that we change the key of the signature scheme. The underlying signature scheme is not only the key of the underlying signature scheme itself, but additionally, it has a random string attached to it. And it is as big enough to encode a share. So in the real world, it will be just a random string. And then what we're going to do in the reduction is that we are going to switch. And we're going to have in this random string an encryption with sort of a one-time pad encryption of the share. So here is how implementing the memory. The memory is all the verification keys of all the parties. And this read from the memory is just decrypting from these keys. So this is how we're going to implement the memory. And then we are also changing the computation of the share, that in the real world, the program will have computation of the share with a normal PRF, which is not a puncturable PRF anymore. And in the reduction, instead, since we have encoded these shares in the keys, we can stop computing the shares with the PRF, so we can forget this PRF key at some point, and we can decrypt from the verification key and output the share. So now I'm gonna try to show a little bit more in detail in the last slide that I have. So basically, in the real world, the circuit is this. So on top, I depict the situation that we have with the keys. So we have n keys, and each of those in the real world is just a pair of a puncturable signature key, VKI, and a random string, RI. And then the program has hard-coded all of the information that it needs, like the commitment to the keys, the reference message, a PRF key, K1, and a puncturable PRF key, K2. And then basically the computation before we check that the commitment is verifying. Fine. And then we compute the corresponding share using the PRF with the KK1 as a source of randomness. Okay. And now the first switch that I want to do, I mean, this is several steps of the actual proof. But anyway, like one step that we want to do is to move from a setting in where a normal keys with a random string to a setting where all the keys are generated by the reduction with an encryption of the corresponding shares. And the computation also of the circuit now it's changed, and instead of computing the share with the PRF key, is decrypting these shares from the keys. So now there is no share computation anymore. So you can see that we are not hard coding the key K1 anymore. We can forget it. So actually the circuit itself, the program itself does not encode information on the shares anymore. We just have the information on the share now in the keys. And now it's much simpler. We have to delete these shares from the keys. So what we will do is that we'll now first do a step in which we switch all the honest keys to have in the second portion of their key a random value. And we do that by puncturing honest signature keys so that there will be no verifying signature for those keys. And so we will able to make standard functionary argument with the security of IO to replace this random string on the right-hand side with this encryption on the right-hand side of the key with a random string for honest keys. And now we're basically done. We can do the last step in which we switch all the remaining corrupt keys to random, and we use the secret sharing security, and we can switch also the message of the ciphertext to the other message of the security key using the INCPA security. So that's the end of my talk. I'm ready to take questions.
Thank you. Very nice talk. Just I have one question related to instantiation.
Yeah.
Your building blocks are SSP hash, pseudo-random, puncturable pseudo-random function, and more specifically IO.
Yes.
So just I'm interested to know what about the instantiation? Means you have motivated us with one example, application in blockchain. So just I'm thinking how practical is it? Because you are using heavy duty crypto tool like IO. How practical is it?
This is not practical at all. It's just a feasibility study of whether you can make this ciphertext compact. But usually, like even the other papers have sort of a secret sharing embedded in it, and have a compact representation of secret sharing is very hard problem.
The SSP hash you can instantiate like PRF pseudo means puncturable PRF also you can instantiate. Only problem is with IO.
Yeah. I don't know if someone else is able to make it practical. I would be happy, but also very surprised.
Thank you.
You're welcome.
Any more questions?
Thanks for the talk. I was wondering if you guys had thought about the question of adaptive security and the main challenges faced there. I was just thinking, I guess recently we've seen like adaptive security for snarks, which use a lot of the same, puncturing techniques. And I was wondering if you had thought about it and kind of like what the main issues would be.
Yeah, I mean, we thought about it a little bit. It's very difficult first because the IO itself is kind of the IO approach itself is kind of non-adaptive in a way. And I mean, there is like a transformation to make it adaptive by guessing, but by guessing you make the circuit size too big. And I mean, there are these adaptive snarks that recently published. They have a place to put the stuff, the security loss. They put it in the CRS. They have exponentially many hybrids in the security proof, and then they're able somehow to accumulate this huge loss and put it in the CRS. But I mean, we like in this setting, we don't know how to address it.
Thank you.
Okay, if not, let's take it. Thank you. Next speaker is Tapas Bal, and let's hear from him.
Hello. Hi everyone. My name is Tapas. I'll be talking about our paper, Registered a Key Beyond Predicates, Attribute-Based Linear Functions and more. This is a joint work with Pratik Datta and Shota Yaman. Okay, so let's have a quick recap of function encryption. So function encryption is a strengthening of the usual public key encryption comprising of following algorithms. So there is a central authority in the system who runs this setup algorithm with a security parameter as input, and it computes a master public key entity and a master secret key NSK. So each user in the system sends a function to the central authority who runs this key generation algorithm using NSK and computes the secret key SKF corresponding to the function and sends it to the user. So encryption can be done using NPK, and it can be done by anybody who encrypts the message in and outputs the ciphertext CPM. Now, decrypting CPM using SKF reveals the functional value of the message in, that is f of n. Okay, so the security of function encryption roughly states that this tuple f, SKF, and CPM only reveals the functional value of the message in and nothing else about the message. Okay, so although FE generalizes most of the well-known public key encryption, such as identity-based encryption, attribute-based encryption, it suffers from this key escrow problem. So the problem is that the central authority holds the master secret key, and it can generate secret key corresponding to any arbitrary function. So therefore, it poses risk towards the long-term validity of the system. In case we have a potential leak of MSK, there could be a permanent damage to system security. Okay, so to mitigate this issue, we propose this notion of registered function encryption, where we run a setup algorithm, which can be run only one time, and we generate a CRS from a reference string. And after CRS is computed, we can forget the randomness that we used to sample the CRS. So the main difference from usual function encryption is that here user can sample their own public key secret key pair, PKI, SKI. And there is no central authority in the system. However, there is a key curator in the system who collects the public key and function pair from each user and accumulates it into a master public key. So encryption is done as before, but whenever new user joins the system, the NPK is updated. So therefore, each user in the system must get a helper decryption key from the key curator, and it needs a periodical updation. And now decrypting a ciphertext requires the knowledge of secret key as well as the helper decryption of the user. So in summary, registered FE supports one-by-one registration, and sometime we require to update the master public key as well as helper decryption. But the total number of updates and the size of MPK, ciphertext, and HSKI vary with order of polylog L, where L is the total number of users in the system at that point of time registered into the system. Okay, so there is another simplified version of registered FE called slotted registered FE. Here we fix the total number of users in the system at the very beginning, like at the time of setup when we sample the CRS. So therefore, there is no need to update any keys because the key curator will collect all the public information from the user, like PKI-FI, and then it computes a master public key and a helper decryption. So therefore, slotted registered FE supports one-shot registration, and there is no update required for the keys of the user. And the compactness property remains the same. So now, roughly, the slotted registered FE, the security says that given a set of function and secret key FI SKI, the adversary gets the information of FIM for all those I from the ciphertext CPM. Okay, so overall, registered FE solves the key escape problem because the key curator is public and deterministic, and it doesn't hold any secret, and of course, SKI only leaves FI of N. So the importance of introducing this notion of slotted registered FE lies in the fact that in a prior work, Hohenberger et al. Showed that if you can construct slotted registered attribute-based encryption, then you can actually generically transform it into a full-fledged registered attribute-based encryption using a transformation like power of two style transformation. So in this work, we showed that this transformation also holds in case of functional encryption. So which means that if we can construct a slotted registered FE for a specific class of functions, then we can actually generically upgrade it to a full-fledged registered FE for that particular class of function. Okay, so prior to our works, the registered FE has been explored in the setting of all or nothing types of primitives. For example, registered IDE, registered ABE, where successful decryption recovers the entire message. So either you get the entire message or you will get nothing. So in this work, we consider registered FE for the function class IP or inner product. So here functions and messages are represented as vectors yi and x, and the decryption reveals or outputs inner product between x and yi. So we also consider an extension of IP, which is called attribute-based IP or ABIP. So here functions and messages are attached with attributes ATTI and policy P, and the decryption reveals the inner product only if the attributes of the user satisfy the policy of the ciphertext. Okay, so in more detail, we construct registered FE for IP and ABIP with adaptive indistinguishable security under GGM or generic group model. We also construct registered FE for general functions with adaptive indistinguishable security under the assumption of IO and SSD, indistinguishable obfuscation, and summarized binding as function. So the ciphertext size and master public key size is in vary with n log n L, where n is the length of the message or the function and L is the total number of users. And the helper decryption key size is constant for IP, but it varies with the length of the function in case of registered general functions. Also, the CRS size is CRS size depends on NL square, and in case of ABIP, all the efficiency metrics depend on the mod of U, where U denotes the attribute space of ABIP. And we can see that the CRS size of our registered FE for general functions depends on log L only. So therefore, it means that we can support exponential number of users or unbounded linear users. Okay, so independently, Frankert et al. Also proposed this notion of registered FE, and they gave a construction of registered FE for general functions under similar setup as well. And concurrently, Zhu et al. Also proposed registered FE for IP with adaptive indistinguishable security under Kelvin assumption. And they also gave a construction for quadratic functions with much better ciphertext size, but with a very selective simulation security or cell star sim security, where very selective means that the adversary must declare all the functions at the time of setup in the. And subsequently, Branco et al. Also proposed registered fee for IP under a Q-type assumption, whose security is shown to hold in this here. But however, their security is selective and their corruption is static. They also proposed registered fee for weak quadratic functions. Here, weak means that the functions to be registered must be declared at the time of setup. That means setup takes the input all the functions to be registered. Okay, so now to construct registered FE for IPFE, we start with a simple IPFE construction of ABDP15. So here the master public key is G to the power T, where T is uniformly random vector, and T also is the master secret of the system. Secret key corresponding to a vector Y is of the form inner product of T and Y, and the ciphertext encrypting the vector X is G to the power S plus X, comma G to the power S. This is an Elgamal style ciphertext with a randomness S. Now we can see that we can compute the masking term, which is G to the power S times inner product of T and Y in the form of G to the power S times the secret. Okay, so let's first construct a slotted registered FE for one slot scheme. That means in this scheme, we only have a single user in the system. So the CRS is basically the same as the master public key. And the single user samples the public key secret key pair as we do in the plain Elgamal scheme. The master public key binds the public key of the user with the function Y. In the form of W, capital W, which is G to the power R plus inner product of T and Y. It also includes G to the power T. And ciphertext additionally includes W to the power S. So now we can compute the masking term as W to the power S times G to the power minus S times S. So I will call it a decryption equation. Okay, so we have to move on. So we have to add more users to the system. So now let's say that we have L users in the system. So each of the user will sample their own public key secret pair independently. And we can aggregate their public key with the functions like we multiply the master public key of the one slot scheme. However, such a naive aggregation will fail because we can rewrite W such that the PK1 and PK2 are registered with the vectors Y1 plus Z and Y2 minus Z for any arbitrary Z. So this means that at the time of decryption, we'll get unwanted information about the message vector X in the form of the inner product of X and Y1 plus Z and Y2 minus Z. So this happens due to the fact that yi is not properly bound to the corresponding index I. And also when we go beyond all or nothing type primitives, for example, function encryption, each user computes different function value from the same ciphertext. So therefore, we need to separate the threads of computation in case of function encryption. So we do it by sampling fresh randomness beta I corresponding to user I, and we add the elements G to the power beta I and G to the power beta IT to the CRS. So the public key of the user is computed as G to the power beta I times Rj, and we can similarly aggregate all the public keys with the functions, and we can compute the ciphertext in value. Okay, so now let's decrypt the ciphertext using a secret key skj. That means the user j is decrypting the ciphertext. So now we can see that we have this okay. So we have this element of the form g to the power beta j rj, So this cannot be cancelled using only SKJ, which is basically RJ. So to get rid of this issue, we use the power of pairing. So we need to cancel beta j from the computation of user j. So therefore, we add g to the power 1 upon beta I to the CRS, as well as we encode our vector t in the target group. And accordingly, we can modify the components of master public key and the ciphertext. So now, if we try to decrypt using this using SKJ, then since we have introduced 1 by beta I to the CRA, so we can see that beta j is removed from the decryption equation. That means the first component can be computed as gt to the power s times the secret key of the user. However, since we have introduced 1 by beta j into the CRAs, therefore we will get components like beta I by beta j in the exponent, right? So these are the cross terms where I is not equal to j. So now we have to remove the cross terms to get the actual masking term, which is gt to the power s times inner product of t and yj. So to remove these cross terms, we add we embed beta I by beta j for I not equal to j into the CRS by sampling a fresh randomness term. So additionally, now the user computes encoding of gamma beta j by beta I with rj at the time of sampling the public. So also following the prior works, we add a helper decryption key to the system, and this helper decryption key will help the user to decrypt the ciphertext as follows. So we also add additional component like gt to the power s upon gamma. And now if we try to decrypt using SKJ and HSKJ, we can see that we can compute this masking term using the pairing operation between g to the power s by gamma of ciphertext and HSKJ, which is the helper decryption key of user. So therefore, we can actually get the masking term, which is gt to the power s times inner product of t and yj. So this is the L slot scheme. However, it is secure as long as we do not aggregate a malicious public. So let's see. Let's consider a malicious public key pkj. Let's write it as uj and vji I not equal to j. So the verification equation is as follows. So now, if we can set this uj vji cleverly, like for instance, maybe we can embed a secret vector z into the public key, then it can be observed that this public key passes the verification equation. And this means that the decryption leaks the inner product between x and yj plus z, although at the time of aggregation, the user j registered yj instead of yj plus z. So this is a problem because we get undesired information about the plain text states. So now to resolve this, we can definitely use NIJIP or non-integrated general knowledge proof system to verify whether the public key is computed following the actual protocol. And this has been done by this concurrent work of Zhu et al. In fact, they used quasi-adaptive general knowledge proof system to verify the malicious public. However, we provide a direct solution using asymmetric pairing. So basically, we make copy of the encodings of beta j rj. So we copy it in both the source groups G1 and G2, and we add this additional equation to the verification process. So now, if we try to verify the public key using this new verification process, then we will see that the verification will not pass. So accordingly, we modify all the elements since we introduced asymmetric pairing. So we have to encode the group elements accordingly. Okay, so now if we try to decrypt using SKJ and HSKJ, the decryption is as before. The first component is computed via the secret key SKJ of the user J, and the cross terms can be eliminated using the pairing operation between G1 to the power S by gamma and HSKJ. Okay, so I will conclude my talk. Basically, we formalized the notion of registered FE, and we propose constructions of registered FE for IP and ABIP with adaptive indistinguished security. Although I only showed the construction of IP due to the time limitation, our paper is online and we can check the construction for ABIP. We have also shown one feasibility result regarding constructing registered API for all general functions. Note that all these constructions are not in the bounded collision setting. It's in the full collision setting. Okay, I will finish my talk with a few open problems. So for instance, it will be interesting to see whether we can build registered API for more expressive function classes such as AWS, which is attribute weighted sum introduced by Abdal et al. In 2020. So another interesting problem is to reduce the CRS size in existing registered API for IP and ABIP, because currently the CRS size varies quadratically with the number of users in the system. It will be interesting to at least make it down to linearly the number of people. So and another problem is that currently the only known attribute-based FE construction in the registration-based setting is our work, which is in GTM. So of course, it will be interesting to see whether we can build it under standard assumption, for instance, maybe lattice or pairing-based standard. Okay, so with that, I will finish my talk, and our paper is online. Please see it if you want. Yeah, happy to take questions now.
I guess so these constructions are proven in the GGM. Is it possible to maybe not in the standard model, but like in the algebraic group model, show it from some standard assumption?
Yeah, I mean, this could also be possible because we were also trying to introduce a Q-type assumption to establish the security of our system. But we thought that maybe it will be interesting to have a more efficient solution for a registration-based system, because you know, when you introduce standard assumptions, generally what happens is like you increase the size of ciphertext and maybe master publicity. So that's why we kept it as efficient as we can using GTM.
Okay, thank you.
Okay.
So you said your scheme is static in the sense number of users are you have to fix beforehand, right?
No. So our scheme is not static. The scheme presented by Banco et al. Is static. So our scheme is in the adaptive.
Any a number of users can join, right?
Yeah, any number of users can join, but in the pairing-based setting, since the CRS size only vary with in L square, so we can only support bounded number of users, but users can join at any time.
Okay.
Right.
Because of your restriction or CRS size, you are
Yeah. It's bounded, but in the feasibility result, as we showed for general functions, the CRS size is order of log L, so therefore we can support exponential number of users. So for that we need IO, of course.
Yeah.
Yeah, so from the constructions, it looks like Q-type assumptions. What is the bottleneck? Like, why you were not able to come up with the Q-type?
No, it could be possible. So as I said that it could be possible to introduce a Q-type assumption, but as I said that we wanted to keep the ciphertext type short, as well as if you can see how to go back. Yeah. Okay, so if you can see the table. Yeah. Okay, so if you can see that our work only achieves the helper decryption key size, which is constant. So therefore, we kept it GGM to achieve, I mean, to see whether we can achieve some constant size elements in this system. So yeah, of course, Q-type assumption is possible because I think Branco-et-al.'s registrative for IP is under a Q-type assumption, but they achieved only selective security under static one. Thanks for that.
Questions? Then let's thank Tapas again.
Thanks.